So if you're looking for me on the internet, you can find me at Surfing Complexities, where I blog. I'm on doing the Mastodon thing, no root cause on the Hachyderm instance. And if Twitter hasn't melted down yet, I'm probably still around on Twitter as no root cause. All right, so the title of my talk today is Why This Stuff is Hard. I had a couple of alternate titles in mind when I was coming up with this. This is one alternate title, Why We'll Never Stop Having Outages. And finally, this other title, You Aren't Actually Doing It Wrong. Now, this is a little bit of a weird talk because I'm standing in front of a room of people telling you why it is your job is hard. And you all already know why your job is hard, but what I'm trying to do today is to kind of give words to some things that you probably all feel like at a deep level, but may not have had the language to explicitly talk about, because I think being able to talk about the things that make SRE work hard is important for us to get better at it. All right, so this is what I'm going to be talking about today. I'm going to start by talking about this thing called the adaptive universe. Then it's everybody's favorite topic, complexity. I will talk about the idea of having only a single point of view in systems. I'll say a little bit at the end about coordination, and then finally wrap it up like, okay, what do you want me to do with this stuff that you've just told me, Lorin? All right, so we're going to start with this thing called the adaptive universe. So the adaptive universe is a model of the universe that was proposed by this gentleman here, who's actually, I think, been mentioned a couple times in this talk, in this conference. His name is David Woods. He's a resilience engineering safety researcher. And the adaptive universe is a very, very simple model of the universe. It has exactly two assumptions in it. One assumption is that resources are finite, and the second assumption is that change never stops, right? And now I'm going to drill into these assumptions and why I'm talking about them. All right, so let's talk about the finite nature of resources. And I have selected here for my image a very nice sort of hourglass picture. And the reason is that the one resource that I don't know about you, but I always struggle with is that I never get enough time to do the work I really want to do at the quality that I want to do it at, right? This is, I feel, endemic to me at every company I've ever worked at. That has been the case. And in addition, there never seems to be enough headcount for us to really do the stuff that we want to do. Maybe in your world, your teams have enough headcount, but wherever I've worked, we're like, no, if we just had more people, things would be a lot better. We'd be able to get a lot more of our work done more effectively. And so there's a problem, though. Even if you get more time and more people, even if you're able to sort of build up these buffers, there's this law, which is also comes from David Woods, which is called the law of stretched systems. And the law of stretched systems says that any system, if it has some additional capacity to it, is always eventually going to be pushed to the limits of that capacity. So if you get more people somehow on your team, and it happens, what will happen is you will be given more and more work until your system is once again working at capacity, right? So this is considered like a law of the adaptive universe model. All systems always get pushed towards their capacity, towards their limits. And that makes it hard, right? In particular, the law of stretched systems means that it is really, really difficult for us to build up what's called capacity, to build up sort of extra buffers of time, or maybe imagine having extra engineers that are just doing non-critical work that you could go and grab them and reassign when you really need them. It is very, very difficult to justify purchasing resources and not fully using them, even if you know that at some point you're really going to need them and it's really going to be painful not to have them. So in particular, this makes life very difficult that we cannot build up capacity because of this thing that we all know, which is called production pressure, right? We all feel the pressure to be able to deliver on the work that we need to do for the business to work, right? So you got to deliver on those features, right? You got to get those features out, but you better not break anything while you're doing it, right? So we're all asked to move fast, but don't break anything. And those two things are fundamentally in conflict, right? The quicker you move, the less time you have to, do extra validation, for example, which means that we're caught in what's called a double bind, right? We are caught between two opposing forces to move, as quickly as possible, but to also move as safely as possible so that we don't break things. And these double binds are one of the things that make our work very, very difficult. Another reason why it's limiting this finite nature of resources makes our life difficult is that one of the ways we get better is through reflection, is through thinking through the work that we did. And when you're stretched for time, the problem is it's really hard to carve out time to do that reflection work because you're always working on delivering that functionality. And I've personally seen this in action in all the orgs I've been in, where a lot more time gets spent planning. So I've done a lot of quarterly planning in my time. I have not done nearly as much quarterly reflecting, right? I feel like if you look at the ratio of those two, we spend a lot more time saying, okay, what are we actually going to do next, compared to well, what did we actually do last quarter? And what can we learn from what happened there? I have not done nearly as much of that as I would like to. And my argument is because of finite resources, we got to get this stuff done, we got to plan for next quarter, we get stretched doing the reviewing stuff, which is where the learning comes from. So the second assumption in the adaptive universe model is that change never stops, right? No matter what we do, we are stuck in this dynamic universe where things are always changing. And that makes life hard for SREs, because I think this is the job description of the work that SREs, that operators do. The job is keep the system up and running, even though these waves of change keep happening, right? And that's hard, right? Because we know that change breaks stuff. And I want to talk about one specific example of that to illustrate why this sort of thing is hard. I'm going to talk about code freezes. So out of curiosity, how many people are familiar with code freezes? All right. How many currently work at organizations that do code freezes? Okay, nice. There'll be one more question a little later on about this. So everyone is actually familiar, but I'm going to be super pedantic and explain what a code freeze is for anyone in the audience who doesn't know. So outages happen. They're bad, but they're not equally bad. We have this theory, which I think is correct, that the cost to the organization of an outage is going to vary depending on when that outage happens. And in particular, there are some times when the cost to the organization is much, much higher. So here's my model. So for example, let's say you're a company that has a Super Bowl ad. If your site goes down during the Super Bowl, that is perceived as being much, much more expensive to the organization as if it went down in some random day in the summertime. Similarly, the holidays, if you're an e-commerce site and you go down during Black Friday, also if you're at companies where it's a little bit quieter during the holidays because people go on vacation more, so they're less likely to be able to deal effectively with incidents. So we all sort of know that the cost of an incident actually does vary based in time, and there's some times where we think it's a lot more expensive, right? And so what do? Because we know that change breaks things. So we say, all right, this is what we're going to do. We're going to play in time with when change happens, and we're going to just dial down the changes that happen during those times when it's really expensive, right? So typically we're changing at some rate, we're pushing stuff to production, and then around the time when it's dangerous, all right, we're going to stop deploying, and then when it comes back, we'll go back to normal. Now we know it doesn't actually look like this, right? Kind of looks more like that, right? So where I work, we call that the quiet period, when you're not making changes. I like to call those two red areas the noisy period, where there's a lot of change, right? So, because we're not stopping the amount of total change, right? We're just sort of shifting it around in time, and we all know that when you bunch up change, that's also more dangerous. So we're sort of playing with things here, and maybe that's actually worse than the other one. And I'm kind of curious about this. I'm actually agnostic, so I don't have a particular answer in mind here. How many people think that code freezes are just an anti-pattern and you really just shouldn't do them? All right. How many people think that they actually have their uses and judicious use of code freezes is good? Yeah, right? It's mixed. It's And this is a hard problem. Like, well, how do we shift the changes in time in order to deal with those risks? This is fundamentally hard. We don't have consensus in our community about whether this is a good thing or a bad thing. I imagine this changes a lot based on context. All right, I'm going to talk about another kind of change now. So my company, Netflix, the SRE team puts out these like weekly summaries of like interesting things that have happened in operations, like incidents and operational surprises. And there was one of these that had a summary that's like blah, 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 blah. The SRE, on a hunch, decided to look at the certs after this. And I was like, whoa, 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 like what happened there? How did the SRE know to look at the cert system? And actually, in this particular case, it was certificate related. It was someone they'd rotated the certs, and like there was some problem with the one that had been rotated that didn't match the clients, and they had to roll it back. And he's like, well, you know, the impact happened globally, and typically we roll out things regionally, so it probably wasn't a deploy. I didn't see any spike in errors in any of the internal services, which is usually, you know, a sign that it's something that's not like a service just broke. And, you know, it happened at around 4 o'clock Pacific, right? And so why does an experienced SRE think about certs at 4 o'clock Pacific? That's midnight UTC. That's when certificates expire. And expiring certificates are a fun class of things that break. And I like this example for 2 reasons. I'm really bringing it up for 2 reasons. One is that, like, you know, change is dangerous, and why do we all know that? We are all sort of like tuned to change, right? When something breaks, you're like, okay, what changed, right? Was it a deployment? Was it something else, right? We know that. We know change is dangerous, and so to get good, we have to figure out like things that have changed if we don't have other signals. The other reason I really like the certificate expiring as a problem that we deal with is that when a certificate expires, the thing that changed is time, right? This is like the world changed around us. You did not make any changes inside of your system when a certificate expires. In fact, it broke because you didn't make change, right? You can't control that change. You cannot stop time. Maybe you can stop time on your one server, but if a client's talking to it and those clocks don't match, you can't do it, right? We don't have full control. Even with code-free stuff, we can have a knob that we can change, we can move some changes around in time, but some are completely out of our control, and that makes life a lot harder for us. We cannot stop change. All right, we talk a lot about systems, and so whenever you're talking about a system, you've got to sort of draw a boundary somewhere in the universe, and things inside the boundary are the system, and things outside the boundary are the environment. And you get to choose where that boundary is. It's not some property of the universe. It's up to you, the system, you know, system analysts say. But one of the definitions of system I really like where do I draw the boundary? So typically we draw the boundary around like the stuff that we can control is inside the system, and the stuff that we can't control we call outside the system and is the environment, right? But like change doesn't care where you draw that boundary, right? Like, so there's always going to be stuff in the environment that you, by definition of how you've drawn your boundary, cannot control that is going to cause you heartbreak, that is going to cause you problems, that's going to break your system. Now, I've been talking about like sort of future changes, things that are currently happening now, but changes have also happened in the past, right? Not just in the future. So here's another question I'm going to ask the audience. How many people here are currently working in an entirely greenfield environment? You came in, it's probably like a new startup, like 0 constraints, no existing code. You can do like absolutely, you get to make all the decisions about whatever you want. You're not stuck with everything. I have 1. All right. So I'm going to assume everyone else is in the other category. So we are all of us, except with 1 lucky person. We are prisoners of history, right? We cannot change the past. We cannot change the decisions that have been made before we got there. And that is one of the things that makes life hard for us. None of us is exempt from this. Okay, I'm going to switch gears here and talk about complexity. I'm not going to define complexity. I honestly personally find like definitions of complexity discussions kind of boring. But I think we all have an intuition that like if there's a lot of boxes and a lot of arrows going between the boxes, that's complex, right? All right, so that's an engineer, and that engineer is dealing with complexity. So I'm going to make an argument here that every time like we make changes to the system to prevent failure modes from happening, often like after an incident, that we are making our systems more complex, that like the nature of our work to increase the robustness of our systems is always increasing complexity in the long run. And so we actually have to increase complexity to make our systems better. And I'm going to make reference here to control systems theory. And the reason I'm going to do that is I think we are all actually in the control systems business. All of us, we build and are part of control systems. We are doing work to keep a system that if we did nothing, it would go down. We're keeping it up, right? That is a control systems problem. So I think there's a lot of concepts in control theory that we can usefully adapt. So I'm going to talk about some work done by this fellow here. His name is W. Ross Ashby, mid-20th century. He's a psychiatrist, interestingly enough, but I know him from his contributions to control theory. And he introduced this thing that has been named after him. It's called Ashby's law of requisite variety. I find that name not like super illuminating, so I will explain it. In one sentence, I also find this not super illuminating. Only variety can destroy variety. So I'm going to actually explain this rather than assume anyone understands that. And I'm going to explain it with respect to this toy problem in control systems theory. This is called the inverted pendulum problem. Right? Imagine you have a cart that can move like sort of left and right, and mounted on the cart is a rod that's rigid, and it has a weight on one end. And it's like sort of mounted, there's like a pivot, and it can fall left and right. And the goal is to push on this cart to keep it balanced, right? So this is an unstable system. If you just hold it up and let go, it's going to fall. But if you push, you can actually keep it up actively, right? So to model this system, you know, in addition to knowing like the masses and lights and stuff, the thing you need to track is just the angle theta there, the angle from the vertical. If you know that, you can actually build a control system that keeps it up. But here's the thing. So let's say you've done that. You've built a control system. You can do that. It knows the angle, keeps track of that. It uses that to move the cart around. And now I changed the problem a little bit. The pendulum can't just fall left and right, but it can also fall forwards and back, right? So now I've switched to the problem of like balancing a broom on your hand, which is also something people can do. It's a control system problem humans can solve. If you use the controller that only knows that one angle, it is not going to be able to solve that problem. It's just going to fall like that, right? You have to make the controller more complex. It has to now track the angle in two different dimensions rather than one in order to solve the problem, because it's going to have to move it in two different dimensions to keep it up, right? So you have to make the system, the control system, more complex because the space that it has to deal with has gotten bigger. Right, so when we build in better control, when like our original system couldn't handle some certain failure mode, and so we now have to add stuff so that it can, even if it's adding an alert, we're still creating a more complex model, right? And so inherently our systems are going to get more complex. And man, when you make them more complex, they get weird. You get really weird failure modes from the things that you have built to keep things actually, you know, handling these failure modes. Now you might say to me, all right, Lorin, I buy that. But really, like in my world, my systems have a ton of complexity, and they're not from this like robustness, like ad control stuff. It's because of like decisions that were made long ago that don't make sense. There's all this like accidental complexity in my system, and if I could get rid of that complexity, my system would be simpler and it would be more robust. And I believe you, but I'm going to refer you back to the adaptive universe, and I'm going to say that like if you could do that, you would have already done it. But the reason you haven't done that is you don't have the time, right? You do not have the resources to go in and to remove that accidental complexity because you're constrained. Now, we're able to add stuff in after incidents because the organization is willing to spend that time after an incident to go add this stuff to it. So you have the org lets you spend the time increasing the complexity, but reducing it is a much harder lift, and in practice, none of us get the chance to do it as much as we want to. All right. Let's now talk about perspective, seeing things from only one point of view. So here's an engineer. She's looking at one part of the system, but the system's actually much bigger than that. And all of us, this is a fundamental aspect of reality. We can all only see one part of the system. There's this entire system that we have to deal with, and we only ever get to see a little bit of it. So as a consequence, we never have full understandings of these systems that we are trying to keep up and running, right? We always only have just partial knowledge about how things work, what's out there, what's changing, stuff like that. One of the challenges here, actually, with partial knowledge is that you can't look at one part, one component, one service, and look at another one and understand how they're going to interact. I can tell you, I've seen many times when this service changes and that causes this service to do something to that service, right? And if you look at those just in isolation, you are not going to see those interactions, but they're going to get you. So some people call this, so once again, David Woods, John Allspaw, they have this term dark debt that refers to this phenomenon where there are these hidden interactions lying in wait in your system for an incident to happen, and you don't know that they're there because you haven't hit them yet. And it's not like tech debt where you sort of feel like, we need to pay down the tech debt. No, you can't even see these interactions because you have not experienced them yet, but they're going to take your system down. So none of us have a global view of the system, so we can't make globally optimal decisions, right, like day to day. We have what's called local rationality, which makes our life hard. People make decisions that are rational based on the information that they have locally. That's the best we can ever do, right? But like that's actually not enough to prevent us from making changes that can break the system. So I would say probably every single incident, you can point to something and say, there was something that somebody didn't know, right? There were decisions that were made and and if only someone had known that, excuse me, it wouldn't have happened, right? So I would say probably like 100% of incidents, roughly, that is the case, right? But like, we're stuck with that. So this, to me, is the grand challenge of software engineering, right? The hardest problem, in my opinion, in software engineering is getting the right information into the heads of the people who need that information. And this gets like sort of exponentially harder as you get larger as an organization. And there's no easy solution. I could spend 100% of my time at Netflix reading docs that other teams and memos that other teams have published and still not have enough context about everything and still not get any of my own work done, right? So this is like an effectively impossible problem that we need to solve in order to do our work effectively, but we have to do it. Another thing that's challenging, and here I'm going to take a quote from a book by Carl Wieck, who's a professor emeritus now, professor of like organizational psychology, studies organizations. He wrote a book about sense making, and here he's talking about the fact that, well, there's a lot of things that sort of propagate in organizations that get passed down, like culture. One thing that doesn't get passed down is the work that people actually do, right? So what he calls action is really like work. And he says the problem is that like work itself is ephemeral. Like when you do it, it's gone, right? You can try to document things. You can capture images of the work, but the work itself is not a concrete artifact that gets passed down. And that makes things a lot harder for us, the fact that work is invisible. And one of the reasons why it makes it harder is it's very difficult for us to be able to watch experts as they're doing their work. And I don't know if anyone caught Paige's talk earlier today, Paige Cruz. It was an absolutely fantastic talk about cognitive apprenticeship, which is trying to solve this problem, which is that naturally we can't watch experts in action, and so we have to actually do additional work to be able to do that. And also, if you saw Andrew Hatch's talk today, he talked about the fact that you actually have to work to make work visible, because it just isn't naturally visible. It's ephemeral. But this is how we get better, right? This is one of the ways is you actually watch experts in context doing their work. And then I'll tell you, like, it's amazing to watch some operators who are really good. All right, the last things I'm going to touch on, this is going to be a little bit shorter section, is the problem of communication and coordination. We all know that distributed systems is a hard problem to solve. It does not make it easier when the boxes are people instead of software components, right? We have to solve sort of a distributed systems human problem where we have to coordinate. In particular, because we all have partial understanding of the system, very, very often incident response is something that has to be done by a group, right? Different people have different parts of knowledge of the system. You have to bring them together to actually solve the problem. So we cannot avoid coordination work. At least, and I'm not even talking about the regular software engineering, just incident response. Coordination is a hard problem. And it turns out that like communication, like effective communication is a really difficult problem. I don't think we appreciate that. I used to think that I was just like not a good talker. I would have a conversation with someone and I would say something and they wouldn't get my intent, what I was trying to say, particularly like on the phone. This is a big concern for me. Then I'm like, why can't I speak well? Why don't, like when I say something, someone doesn't understand what I'm trying to say? And then later on in life, I discovered, well, like this is just hard. And like in conversations, people are always like doing work to repair misunderstandings between things, right? This is just a natural thing that people have to do because communication is actually a really, really difficult problem that I think we don't appreciate because we're generally pretty good at it. This gets even worse if you're now in like a hybrid world or a remote world, and some of you are communicating over channels like Slack or Teams. I'll give an example of this. There was an incident that I was sort of like a bystander to. It involved a service that we were a dependency of, so like a sibling team, and I was like hanging out in their on-call channel. And I know the guy who was on call. He's a really good guy. And he puts this message in the channel. He's like, anyway, we're dead in the water until this figures itself out. And I was like, what the hell? You're just gonna like sit there and like hope this service comes back up? Like, what are you doing? And what had happened is he had gone and like some piece of infrastructure had gotten wedged and he failed over from the primary to the secondary and it was an active passive system and he was waiting for the secondary to come up, right? And that's what his intent was to communicate. But I didn't know that that's what he had done because work is invisible, right? I didn't see him do that. We're not in the same place. We're over Slack. And that was my interpretation of this, of that Slack message. And I was kind of agog, but like he was more senior to me. I felt weird saying anything, and then eventually it came back. But it's just an example of how hard this is. So that's all I'm actually going to say about communication and coordination piece. Fortunately, this person, Dr. Lorin Maguire, is here. She's giving a talk later on in this session. Her PhD dissertation work was around coordination. She's giving a talk today, so I'm going to defer all the great, like, how coordination is hard and what to do about it stuff to her. I encourage you to go hear her talk. All right, so I'm going to wrap this up now. Okay, so I've told you why things are hard now, and like, now what do you want me to do, Lorin? So just to wrap up, so one, we can't escape. We're stuck in the adaptive universe. We always have finite resources. We can't stop change. In the long term, complexity is only going to go up in all of our systems. We can only see the world from one point of view. None of us get to step outside, be omniscient, only have partial understanding of the system. We cannot do this work alone. We are always going to have to coordinate with other people to do this sort of operations work, and coordination is hard. So these are all effectively constraints that we have to work under in order to do our work effectively. Right? And so we can't get rid of any of these constraints, but what we can do is we can get better at navigating these constraints, at working within these constraints to do well. Right? And that means, like, to me, like, this is the one takeaway here, is I think like we need to, as much as possible, treat the skills involved in doing operations work to be a first-class thing, because we cannot eliminate the constraints, but we can get more effective at working within those constraints. And I think that is really the best that we can do. And I will leave it with this. This is a quote from Jon Kabat-Zinn. If you've heard of him, you may have heard of him because he's very big in like mindfulness meditation. Interestingly enough, he has a PhD in molecular biology, so I'm putting doctors on everyone else who has them, so he gets one too. And he said, you can't stop the waves, right? We can't stop change, but you can learn how to surf. And that's it. Thank you.